Okay, so we're told that for this circle, the area is a 100 pi SU. And the SU represents square units because with area, we deal with square units. So we don't know what the units are, but it's 100 pi square units. And before we even really read the question, right, we can pick apart the area to understand some other basic things. Remember that the area of a circle is equal to pi times the radius squared. If I reverse the order of these two variables, I get radius squared times pi. And then you can almost see, oh, we have 100 pi, so the radius squared must represent the number 100 because we're multiplying it by pi, and that's correct. Here, radius squared equals 100. So the radius equals the square root of 100, or 10. And if it doesn't convince you, we can set these things equal. Radius squared pi equals 100 pi, right? Solving for radius, we first divide both sides by pi. And then we get that stat that r squared equals 100, and then the rest follows. So we know our radius is 10. And then what I would do is maybe even label that, right? Any line from the center to the circle is a radius. So this is 10, that's a radius, and so is this. The next thing they tell us is that the measure of arc ADC is 240 degrees. So this large arc right here is 240 degrees, almost the complete circle. So then I would say, well, what's this arc right here? Well, the measure of arc AC is the remaining degrees. It's 120, right? 360 degrees minus 240 is 120. Now this angle right here is a central angle, an angle formed in the center of a circle by two radii, and it equals in measure to the arc that it intercepts. So the arc that it intercepts is this arc right here, AC. It equals that in measure. This is 120 degrees. So we're already on our way to labeling a lot in this circle. They want to know, what is the length of ADC? So here they're asking you for a measurement in radians, and then they want the area of triangle ABC. So we're going to deal with this in radians. So how do we do that? Well, really quickly, we are equipped, we have information in degrees. We need to convert that into radians, right? So what is the degree measure of ADC? The degree measure of ADC, arc ADC, it is equal to, they tell us, 240 degrees. Well, every 1 degree is equal to pi over 180. So in terms of a ratio, right, if every 1 degree is pi over 180, right, if I had 2 degrees, it would be 2 times pi over 180. If I had 3 degrees, it would be 3 times pi over 180, and so forth. So if we have 240, we just multiply our degrees by pi over 180, and that is equal to our measure r in radians, or excuse me, depends how this is written, I guess, but I guess we could say that this is equal to s, right? That's usually, I think, the variable reserved for arc length, right? S is for arc length. So here, 240 times pi over 180, leave pi as a constant, using the symbol pi. You don't have to deal with that. So we have really 240 over 180 times pi. And we just reduce this to get the value of s. 240 over 180, I think you can see that 60 goes into 240 4 times, and it goes into 180, right, 3 times. So here, it's 4/3 pi, and that is the length of the arc. Here, altogether, right, an entire and complete circle would be the circumference, if you think about the length of a circle, right? And to understand a little bit about what this means, and you might have worked with this before, but I think some background can help when converting to radians to understand what's going on here. A radian is a measure in terms of a radius. So if we have a circle or a portion of the circle, and we're looking at some kind of a segment, right? So these are 2 radii. This is a radius here and a radius here, r and r. And we want to know how long is the arc that it intercepts. Well, it depends, right? If I told you, we're looking at the measure of this angle in radians, and I said, well, each radius equals, I don't know, 4 feet or something. And you could see this is about to scale. And if I ask you, how many of these radii would it take to span across this arc? Well, it's about one here, 4 feet, and another 4 feet here. Pretend I'm drawing this perfectly to scale. So you could say that this arc is 8 feet long, or you can say that it's equal to 2 radii. And that's why they would say this is equal to a measure of 2 radians. That's an angle measure. So another way, let me write this over here, another way of writing an angle measure is to say how many radians it is, or how many radii, excuse me, it would take to travel across the arc you're looking at. Now, the variables we deal with, right, this arc right here, this length, is called S, as we called it up here. This symbol theta is usually used for the angle measure, and R is used for radius. So if I said how long, right, is this arc, S? Well, and we wanted to, if I said to you, we're given an arc length S, and if we know what the radius is, how would you find the measure of the angle here? Well, think about what we just did. We found out how many radius go into the arc S. So it's S divided by R, and that equals theta. How many radiuses divide into the arc length S? And that's the measure in radians. In this case, it would be 8 divided by 4. 8 is S, 4 is the radius, so radians is 2. And that's our measure here. Now, to convert between degrees and radians, just think, oh, well, what is the largest degree measure that we can get in a circle? Well, it will be the full circumference. And circumference, right? Circumference is a full 360 degrees. And the formula for circumference is 2 radius times pi, right? Or diameter times pi. And here, if we say, oh, let's mess around with this formula a little bit. I want to look at S. I want to isolate S. So multiply both sides by R. So originally we have S over R equals theta. Multiply both sides by R. It's cancel out. Then we have this formula that S equals theta times R. And here, if we're saying S is your largest case, it's the full 360 degrees, right? Well, what does that mean? Well, that means here, if we plug in 360 degrees, right? If we plug that number into our formula, we can actually find out how to convert between radians and degrees. That's really all we need to do it. So let's do that. So if S equals theta times R, and we're assuming S is the full circumference, that's 2 pi R, equals theta times R, can we do anything with this? Well, yes. Here we have R on both sides, so I divide by R, right? Divide by R, cancels out. And here we know our angle measure. We know we're saying it's the full circle, right? 360 degrees. So we can think of theta either in radians or degrees. We know the full circumference is 360 degrees. So instead of putting in theta for our angle, we can put in 360. And that equals 2 pi. If I want to know what pi equals, I divide both sides by 2. And now you get this really important staple in radians and degrees. Pi equals 360 over 2, or pi equals 180 degrees. And this is really useful to know, that the measurement of pi equals 180 degrees. And to get the major conversion that I used, that 1 degree equals pi over 180, I took this and divided both sides by 180. And that gave me 1, right? So divide by 180, divide by 180. These cancel and get 1 degree. And 1 degree equals pi over 180. So this ratio is super important in converting between degrees and radians. And using this step right here can help you go back and forth. So you can kind of deduce it through all these steps. And I would kind of maybe rewatch this segment or pause it and try to recreate that on your own to understand the importance of what we're saying here. So all of this gives us our measurement here of 4/3 pi, right, for the larger portion of the circle. Okay. What's next? The area of triangle ABC. Well, we know two radii over here. We know this angle of 120. There's a lot of things we know, right? A lot that we can do here to understand the area of this triangle. So the way I dealt with this, right, is to draw a perpendicular line right here. Just draw one that's perpendicular, and that bisects this line. And once you do that, you get a right triangle. Right, so I'm drawing a line that gives me a right triangle here. And let me just, that's not very neat. Let me use my line tool, sorry. So, line here, it's perpendicular, I get a right triangle. And I have an identical one on the other side. So, what do we know about this? Well, this is a very special triangle, right? Because if I draw a line here that cuts this in half, that bisects it, it wouldn't be 120 degrees. In here, I would get 60 degrees. And then I have 30 degrees left here. So I have a 30, 60, 90 degree triangle. In a 30, 60, 90 degree triangle, right, the hypotenuse, which we have right here is 10, is always double the shorter leg, or the leg opposite of the 30 degree side, 30 degree angle. So this is 5. So now we can figure this length out using the Pythagorean Theorem, right? 5 squared plus b squared, we don't know what that is, equals 10 squared. 10 squared is 100, minus 25 or minus 5 squared equals b squared. B squared equals 100 minus 25 or 75. And b would equal the square root of 75. I'm going to break this root down because that's 25 times 3. So it's the square root of 25 times 3. What's the square root of 25? That's just 5. We have 5 radical 3. So this length right here, which is half the total base, is 5 radical 3. So the total base, if we add the whole thing up, right, this is half the base, would be 10 radical 3. How do you find the area of a triangle? It's base times height divided by 2. So 10 radical 3 is our base times our height, which is 5, and then that's divided by 2, right? So 10 radical 3 times 5 is 50 radical 3. Divided by 2 equals 25 radical 3. And that would be the area of our triangle. Alright, hope this helped.